I will begin with a word of prayer. Dear Father, we thank you for this day again, Lord. I thank you for these students. Just pray that you be with us today. Help us to, again, glorify you, Lord, in what we do. In your name I pray, Lord Jesus. Amen. All right. Let's see here. So I think what I wanted to try to help you guys with, not sure if you want my help, but all right. So the main thing I'm wondering about is what is an actual reasonable strategy for finding the Jordan or the rational canonical form for a given matrix. I'm relatively certain at this point that for a specific 2x2, specific 3x3 or 4x4 matrix, I want to say that the Smith normal form calculation over the polynomials with x is probably not a good approach, especially for a test. Like, almost certainly the way to do it is to find the minimal polynomial and extrapolate from there. To my opinion, that's the way to go. Now that said, one of our goals in this take-home test is definitely to understand the Smith normal form and the calculation which is given in Dummett and Foote. So I don't want to give up on that. I'm just trying to tell you, as far as the final goes, don't do it. Okay? Unless there might be a problem in the final, which is, here's a matrix, find the Smith normal form. That would make a decent question. What would make an indecent question is, find the rational canonical form from the algorithm outlined in Dummett and Foote for using the Smith normal form. That would be an indecent question. There's no room for that in polite society, I think. Let's see here. So I thought the first few ones in here were fine. Let's do a class survey. What do you guys got for number 10 so far? Now, Jess, you said you got Z plus Z2 plus Z8. Okay. And Daniel, you were a little bit fuzzy on yours, so Z plus Z2. Well, by consensus, we got a Z2 in there. Z plus Z2 plus Z3. I like that one the most because that's what I reverse engineered.
If you do the Smith normal form, you can't have Z3.
Oh, sorry. But I like your answer in that is that's how I made this problem. But yes.
The thingies on it, I got 1, 2, 3 down the diagonal.
Yes, those thingies that you did are fine, but the thing is about the thingy that you ended with is not the Smith normal form, because we have to have the divisibility.
There is the thing though, like you can have like the matrix like that technically be correct, but I think like you'd have to do like a sort of thing in there and it's like a modification, so you can get it to the lowest possible number such that the previous number divides the last number.
Right.
And so work it out. We might be able to turn that 3 into an 8, possibly.
3 into a what?
We got 3 into an 8.
To an 8?
Well, not 3 isn't equal to 8. I might be able to find a link that I found that on, but it shows you like a 3-step trick to turning it into something.
I believe that the 2 and the 3 can be turned into a Z6. Yeah. But anyway, I think it's safe to say that all of you need to rework that problem carefully and then compare your results. Right? Okay. Yes, the consensus is that we all need to calculate that one more carefully. All right. So I don't really have anything to say about number 1, number 2, number 3, number 4 in terms of the test. I think these are pretty straightforward. Characteristic and minimal polynomials, I think you can figure those out. Was the one we were just talking about, Leah, number 11? So for that one, my advice there would be don't use the Smith normal form thing. The strategy you want to go with is to calculate the minimal polynomial and extrapolate from there. Number 6, which is number 11. Number 11 and 12.3, possibly number 22 and 12.3. Do not be dogmatically using the reduction over the field of polynomial stuff there. It's better to think about like the examples we did in class where we just figured out what the minimal polynomial was and did stuff with it. You know, the fact that the characteristic polynomial and minimal polynomial share the same factors. This linear algebraic thinking is the way to solve those, I think, not the Smith normal form stuff, okay? So, number 9 I worked out. That wasn't too bad. Number 8 I'm stuck on at the moment. Number 11, I'm going to start with that because Lorenzo is still a little bit fuzzy on what I mean by that. So here's a different one. A little bit less writing, but let's look at the A is equal to the direct product of the complex numbers with the complex numbers. Okay, so this animal right here, in terms of its native formulation, is like this: ZW times, you know, AB, if you like, is ZA WB. So both of these are just multiplication where? In the complex number system, right? It's the same complex number system. I'm not using like I for one and J for the other or anything like that. It's not like that. Okay, so the idea I have basically to create a representation for it is to find a corresponding algebra B, which as a point set is going to be R4. And I want to pair that with some weird multiplication, let's call star, which has the same algebraic. It really is the C cross C multiplication written in 4-dimensional real notation is all it is. So all that really, you know, to do that, all right, is what I do is I look at, let's say, x1 plus iy1, and then let's say x2 plus iy2, and then I'm going to multiply that by a1 plus ia2, b1 plus ib2. All right. So when we do this multiplication, what do we get? We get, we get x1, a1 minus y1, a2, right? Plus I times what? y1, a1, right? Plus x1, a2. That's my first. I just multiplied first component as first component, use complex multiplication. And then this one times that one gives me x2 b1 minus y2 b2 plus I times y2 b1 plus x2 b2. So essentially what I do, I mean, honestly, I guess to be a little bit more sort of pragmatic about it, basically I'm introducing a coordinate chart that goes from C cross C to R4. And the basis I'm going to use, it's kind of a standard one. It's E1, IE1, E2, IE2. So if I look at, you know, what's the, let's see here. So for example, the coordinate of x1 plus, well, let's look at the coordinate of a1 plus ia2, comma b1 plus ib2. What is the, with respect to this choice of basis, what's the coordinate map give us? How many copies of E1 do you got there? I mean, this is literally A1E1 plus A2 times IE1 plus B1 times E2 plus B2 times IE2, right? So these are the coordinates. with respect to that basis, and I can just write down A1, A2, B1, B2, right? Are you guys with me? So this is essentially all I want. I want that phi of, Z1, Z2 times, I guess, W1, W2, I want that to be phi of Z1, Z2 star, phi of W1, W2. So here, this is the multiplication in A, and over here, this is the new multiplication in R4, which I'm calling B. And essentially, I'm arguing that I can make this the definition. I can use this to define the star multiplication. So this was my Z1, this is my Z2, this is my W1, this is my W2 I'm thinking about, okay? All right, so what I have then is the following. I have that this I have worked out right here. It's exactly x1, a1 minus y1, a2, comma, y1, a1 plus x1, a2, comma, x2, b1 minus y2, b2, comma, y2, b1 plus x2, b2. That's the R4 version of the product. And on the other hand, that's supposed to be equal to this, which was x1, x2, excuse me, x1, y1, comma, x2, y2, star, a1, b1, a2, b2. So now all I've done is to find an isomorphic copy of the algebra, which is more convenient to think about producing a representation from. What is a representation? It's either a set of linear maps or it's a set of matrices which is homomorphic to the given algebra, right? So it's easy to find matrices from this which are going to be homomorphic. So like all I do is look at 4x4 matrix. I can look at a 4x4 matrix. I can think of this as, I guess I need yet another, I don't know what to call this stupid thing, M. This is the matrix representation of Z1, Z2, okay? And that times, well, A1, B1, A2, B2, all right, that should be equal to x1, a1 minus y1, a2, y1, a1 plus x1, a2, x2, b1 minus y2, b2, y2, b1 plus x2, b2. So my point is, once you find what your algebra looks like realized on Rn as sort of an abstract multiplication, which I usually use star for, you should be able to work backwards to what matrix gives you that same structure. At this point, it's a standard matrix calculation. Like, what do I put here to give me that? You guys tell me, right? Mm-hmm. Yeah. Minus y1. Okay. 0. And then the next one is what? Yeah. All right. And then down there? Yeah, 0x2. Okay. Negative y2. Huh. That's funny. My choice of basis is unfortunate in some sense, right? If we swap things around a little bit, we'll get 2 by 2 blocks, right?
Yes. So if you did A1, A2,
Yeah.
wait, we'd pop it over here. Right there. Right on the line. Why'd you switch it?
Did I switch it? Oh. Wait a minute. A1, A2. What have I done? Oh. Man, guys, don't do that. Come on, guys. You guys gotta stop me before I get that far into it. Come on. You're killing me.
We get the concept.
You got the concept. I worked through this matrix. I'm like, I'm gonna be slow and careful on this one. Oh. You guys, you gotta stop me. Left to my own devices, this will happen. All right, so yeah, I was like, well, it's really weird. Well, mathematics is a team sport. So, was Sprano back there fuming when these things were said? I felt like, no?
He was grading. I don't think he was paying much
He was grading?
Yeah.
Ah, okay. Well, that explains it. Yeah, so that's what I wanted. There we go. Hooray. Okay. Yeah. There's part of a larger pattern going on here, guys. So like if you look at the R cross R, if you look at R cross R as an algebra, let's say, then the regular representation of this looks like this, right? And in some sense, we call this A tilde. If we take C tensor A tilde, what do we get? Well, we get C cross C, right? And what is that? I mean, that is like this tensor, you know, it's something like this, right? Tensor, that's still not quite the right time. It's things like this anyway, right? And there's some kind of pattern going on here I haven't fully explained, but anyway. All right, hopefully I've said enough anyway so that you can do that problem. I'm sorry it's so awful. I could have made it smaller. So sorry, what's done is done. Like, I don't know, I guess this would make a better final exam question, right? Okay, something smaller, much smaller. what would make maybe even a better final exam question is like, here is a mapping, prove that it's a, prove or disprove that it's a representation of the algebra or group, right? That's a little bit easier for me to grade because there's 8 of you and there's like infinitely many homomorphisms you could come up with. The grading could get kind of hairy for me. So, all right, enough of this. Let's get back to number, what is it, number 8 is the offending problem. Shall we work on number 8 together? Daniel, are you going to help me? All right, you'll guide my steps. Okay, I will definitely allow it. So this one was supposed to be, like, I was trying to find something. All right, so this one, first of all, you guys, setting aside the instructions that were given, right, this thing. Set aside the instructions that were given. If you ignore my instructions and just say, could you put this in rational canonical form? Here's how I would do it. I would say, aha, we have lambda equals to 2 thrice, right? So then I would calculate a minus 2i. That would give me 0, 0, 0, 1, 0, 0, 0, 1, 0. So a minus 2i squared, 0, 0, 0, 0, 0, 0, 1, 0, 0, a minus 2i cubed, 0. So from all of this, I would learn that the minimal polynomial of a is exactly x minus 2 cubed. And once I knew that, then because of the theory of minimal polynomials and everything that's discussed, that tells me that that the rational canonical form is got 1 3x3 block. And so basically this is a x cubed minus 6x squared plus 12x minus 8, yeah? And so 0, 1, 0, 0, 0, 1, and 8 minus 12, 6 is, in fact, the companion matrix to your minimal polynomial, and that would be the rational canonical form. And to find such, to find the change of basis to get from there to there, you know, to find P inverse AP equals to this thing, all I've got to do basically is find an x such that if I use x and if I use ax and if I use a squared x, if I use this as my basis, then if I can find such an x, then this will give the p, which similarity transforms it to the rational canonical form. I use this kind of cyclic basis will get me where I need to go. For example, well, anyway, I want to. That's just a sketch. But the thing is, I don't have a good advice for you on how to find x. Do you know, Daniel? How to say? I mean, I can tell you this: if x is going to be what we want, it's definitely not in the null space of x. Better not be in the null space of a, and it better not be in the null space of a squared, right? And so I've experimented with this particular problem, and I was just able to select an x and get it to work. And I've actually completed this numerically, this way of doing it. But again, this was supposed to be an easy problem to illustrate the procedure in Dummett and Foote, so let's try to work through that. Because certainly we all need more practice on calculating the Smith normal form, heaven knows. Let's see here. So where we go? We start with, what are we supposed to start with? Xi minus a, right? Which is x minus 2, x minus 2, x minus 2 down the diagonal. And you got your 1, well, minus 1, right? Minus 1's on the subdiagonal, 0, 0, 0, and 0. So what's the first step in the algorithm? We look for the greatest common divisor of all the entries of the matrix. What do we get? 1. Okay. So that means we need to put a 1 in the upper left hand. So I thought row swap to start. Am I wrong? I'm wrong?
Yeah, sorry.
Okay. I realized that this is an ambiguous interchange of grammar S here. So -1, x minus 2, 0. And I should mark that down because that matters for the construction of the p prime. So that's a row 1, row 2 swap, yeah? All right. By the way, I'm actually following the algorithm on what page, Daniel? What's that? Because I don't think I'm following my own advice. The algorithm I actually wanted you to follow was. Well, do you want? We could do it with the harder algorithm if you want. Do you want to do it with the harder algorithm, or do you want to do it with the one that Daniel got to work? Let's do it with the one where you got to work. I mean, either one would be fine. Let's say it that way. If you've done it the other way and you got it to work, great. More power to you. You can save that. I don't think that's the case for anyone here. So, no harm, no foul. And the effort you've put into Smith-Jordan normal forming it, or whatever you want to call this, is also good. Canonical forming. So the actual algorithm I am speaking of is on page 481 to 482. There is yet another algorithm on page 483 to 484. I digress. Okay, so
You want us to use the 1 and 41.
I think that one would be, well, I'm essentially going to do that one right here, right now. So let's, I mean, if you want to go do the other one, I'm not stopping you.
43 follows the 1 on 41.
Oh, it does?
Yeah, that's an example.
Oh, so you're saying that 480, you're actually saying I'm not disagreeing? It's the same thing? Yeah. Oh, see, because at the moment it looks different to me. Because he's got this p prime, but then over on the other one he's messing with the generator. You know? So on page 484 he starts with E1, E2, E3, and he's doing these various steps to it. Right. So your point is that's exactly p prime. It's the same thing. Okay. Hey, well, hooray. So yeah, this is and this is really the whole point of why you're in the math major, isn't it? See, because this is what using Mathematica or Wolfram Alpha without a math major is like. You never know the difference between things. So what we would think is totally different algorithms are actually the same one. It would be totally hidden to you. You know, there's a false argument made against learning math these days that the computer can do it. You know, but the computer doesn't do it with understanding. And just because someone understood the computer to do it, Lorenzo's like, but you're not understanding what you're doing right now. So it's not a very good example.
Oh, that's not the thought that was going through my head.
Uh-oh.
It was a different thought.
Different thought. I'm not, I'm going to let it go. All right, so,
You implied that we are doing what we're doing with understanding.
Oh.
I found that amusing.
wait, but you will understand what you're doing when you do it. Let's see here.
Is that a threat?
Understanding will happen. I'm sure of it.
Or it will not pass.
Or it will happen again next year.
Low enrollment in this course is always a problem. If I can recycle a couple of you. I mean, for example, we got Daniel to, come back another year, so that worked. Let's see here. It's a slightly different story. But where was I? Oh, what's my next step? Should I fix that -1 to become a 1? Okay, so minus that, and that's important because that will influence our changing the p prime later. So that's I guess I'll write that 2 minus x. Okay, so what's next? What's next in this mad story? What do we do next? What's that?
Clear off the first row or first column.
So column operations, those don't cost us anything for our p prime. which is nice. So we're going to do column 2 plus x minus 2 times column 1, right? But I guess what's interesting is what happens here, isn't it? So we get an x minus 2 squared from that, don't we? And okay. I'll put a divider in just to be safe. Now, do I want to clear out that x minus 2? So to clear out the x minus 2, I need row, what do we? Minus x minus 2 times row 1, yeah? Okay, so that's, we still got our 1, 0, 0 up here. And that's going to give us 0. We got 0. I guess it's kind of, see, it's the interesting thing is it's kind of a non-event, it's almost uneventful. Oh, wait a minute, is it? What happens here? What? But don't I get, oh. You see, this is why I had trouble with this calculation this weekend. That's not, we shouldn't blame the children. Let's keep the children out of this. Let's see here. Okay. At this point, we should find the greatest common divisor of these guys. What is it? It's still 1 because there's that minus 1 here. So row swap, swappity swappity. Let's see here. So row 2 swap row 3. Sorry, I was going to give you guys an example which wasn't your actual problem, but you know, time is an issue for me this week, and so here we are. You too. Let's see here. So x minus 2 squared. 0, yeah. And let's see here. Then we do, I guess I'll do minus row 2 next. 1, 0, 0, 0, 1, 2 minus x, 0, x minus 2 squared, 0. All right, then what? Clear out the columns. So we do column 3 plus x minus 2 times column 2, right? So that puts a 0 here. And then down here we get something interesting, right? Which is what? Oh, that's how we get the x minus 2 cubed down here, eh? Now, Jess, you were awful close to this. I mean, Jess was like a step off from it. He was really close. But he also had a wrong answer, which was far more interesting in terms of the p prime construction. What's that? What's that? I know. I really wanted your wrong answer to be right, because if it was, it would have made the whole like next step in the algorithm so much more interesting. You know? Oh well. So we get rid of that. How do we do that? Row 3, right? Minus x minus 2 squared times row 2, yeah? And that gives me the final product, right? Finally, lo and behold, yield Smith normal form. Hooray! Oh, but but I thought you had something.
Before that, I said I'm guessing it would look like this.
Oh, okay. I'm sorry. I don't mean to malign your solution. Yes, that's good. So, I mean, heaven knows I didn't get it. I have my excuses, but you know, still. Oh, I shouldn't have erased that. Well, I still got them over here. All right. So, Now the algorithm at this point is a little, how would you, so we have to basically convert all row operations to corresponding column ops on the identity, right? And so, let's see here. So we start with 1, 0, 0, 0, 1, 0, 0, 0, 1. And now I'm going to follow the template. All right, so first of all, we have a row 1, row 2 swap, which gives us a column 1, column 2 swap. That's the first thing. All right, what's our next move? Minus, so that minus row 1 gives us minus column 1. So we must have made some silly arithmetic mistake earlier, Jess, right? Weren't we trying to do this?
You did this part after we did this matrix.
Oh, okay. But maybe something in here was wrong. I don't know.
I mean, we got the right matrix, though. I think we had this.
We got this, but I'm not sure our p prime construction was correct.
Yeah. Well,
Yeah.
I think we know it wasn't correct.
Yeah, I'm pretty sure it was. Yeah, fair enough. We didn't have 0 in the first column, so yeah. So where are to we just so you can keep score here. This is 1, this is 2. So this is for the first one, that's for the second row operation. Where's my third? Right here. Now this is where it gets a little bit funny. So for 3, I'll write out in words here. We've got row 2 minus x minus 2 times row 1. And so what he says is you take, goes to what is it? Goes to row 2 again, right? So he says, if I remember right, we take column, is it column 2 of p prime? Oh, that one. Okay, so column 1 of p prime. Is that right? But what about the p minus 2a? Don't we take a minus 2i, right? Times column 1 of p prime, yeah? Column 2 of p prime?
Yeah, column 2. Plus
Plus column 1 of p prime, and this is the brand new column 1 of p prime, right? Yeah. So that is, what is that? Well, that is 0, 1, 0, 0, 0, 1, 0, 0, 0. What's column 2 of p prime? 1, 0, 0, right? Now, the p prime it refers to the last step in the column reduction, right? Okay. So that plus column 1, which was 0, minus 1, 0, goes to what is that? Right there is our mistake, Jess. I believe that was our mistake. My mistake, mostly. So anyway, if you'll allow me to put that up here. So next we get 0, 0, 0, 1, 0, 0, 0, 0, 1. My enumeration, my reading of that matrix is in a very, very non-standard fashion. You should look at it. So that matrix is where we are to now. We just did number 3, and here's this one, yay! I love row swaps, they're so much easier. So step 4. What was it? Oh, 2, 3, column 2, 3 then. So column 1 stays 0, column 2 and 3 go flippity floppity. 1, 0, 0, 0, 0, 1 for the middle column. There we go. All right, that was number 4. And where are we? This is 5, step 5. That one's simple enough, right? So if we multiply row 2 by minus, that corresponds to column. I mean, there's good reasons for these things in terms of how the matrix relates to the generators and so forth and so on. Come back and watch my lectures 5 years from now. It'll make a lot more sense. Let's see here. So 0, what was I? 0, 0, minus 1, assuming 0, 1, 0, 0. Christ hasn't already come back. Let's see here. That does nothing. And one of these again. I hate these. All right. So let me figure out how this works here. Oh, fine, I'll do it over here. So for 6, what do I need to do? I need to take, which is what? Row 3 minus x minus 2 squared times row 2 goes to row 3 again. I'm supposed to take a minus 2i squared times column what? 3, right? Column 3 of the most recent p prime. And I'm supposed to add that? Oh, I had this minus made a plus here. But you notice now, I still got a minus, so it becomes plus. I mean, beware, if it was plus, we would put minus, But because this is minus, I put plus. And then what? Plus column what? Column 2 of p prime. That's my brand new column 2 p prime. Now, of course, this is the very, very subdiagonal, the doubly subdiagonal one in the lower left corner. That's it, times column 3, which was 1, 0, 0. And then we're supposed to subtract 0, 0, a minus 1, which is 0, 0, 1, minus 0, 0, minus 1. Hooray! Well, minus minus gives me add, so I think I don't disagree with you.
But weren't we supposed to add?
Oh. Fine. So, oh man, this is very, really? Is that it? This is it? This is the p prime I've been looking for all this time? It's kind of a loser of a matrix. Is that it? Is that what you got? We're not done yet. I mean, this is actually not, this is not p yet. This is a step on the step towards the construction of P. What's next? There's something else beyond this. Now we have to, as a check on our calculations. Now Justin and I knew we were wrong earlier because when we calculated it, we had 0 in the column 2, but we had a non-zero first column, which is no bueno, according to the algorithm. As he mentions, a convenient numerical check is that you have the 0. So. Where are we? Page where? All right. We have now made it all the way to part 3 of the algorithm. This is very exciting. When xi minus a has been diagonalized in the form of theorem 21, like so, the first n minus n columns of p prime are 0, providing a useful numerical check on the computations. Then the remaining m columns of p prime are non-zero. for I equals 1 to m. Multiply the ith non-zero column of p prime successively by a0, a1, a2, all the way up to d sub I minus 1, where d sub I is the integer in 1 above. So apparently d sub 1, there's only one of them, is 3. So we're supposed to... Oh, in other words, this is very cool. This is the x I was looking for over here. That's why this is neat. That's why this is neat. This is, I mean, it's kind of a long journey, but this is the x I was looking for in our initial discussion. That's what this algorithm is doing for us. This is finding the acyclic basis generator for each block. The cool thing is if you have multiple blocks, it finds all of the generators for each block from the remaining columns. Okay, I'm starting to become a believer in this algorithm again now that I have actually successfully been helped by students to calculate one example of a small 3 by 3 nature. But in my heart, I know that we can do more. Let's see here. If I give each one of you a different matrix on the final, then I'll have like 8 more examples of these, right?
Yeah, then you'll have
Yeah, there you go. If you do a whole final, that's 8 problems.
Then you'll have
No,
like,
no,
one problem. We can trade.
Well, you're not taking any other finals on my final exam day, right? So you can spend the whole day on it, right?
Yeah, I have other finals.
You have other finals?
I do. 8-page paper.
Lorenzo, are you taking other courses this semester? You've been cheating on me. How dare you?
Don't worry, I'm not.
Horrified. Okay, so actually, with this in mind, the basis that we could use would be 1, 0, 0. What happens if you do a times 1, 0, 0? What do you get? Oh, I forgot my a. Where's my a?
2, 1, 0, 0, 2, 1.
2. Oh, I'm sorry.
It's like columns.
Okay, so a times, this is a, right? So a times e1 is what? It is 2, 1, 0. And to find a squared on e1, we can just multiply the second one times a again. What does that give us? It gives us 4. What's that? 441, okay. So in other words, the p, which gives me the similarity transformation that I want, is this one. 1, 0, 0, 2, 1, 0, 4, 4, 1. Now, in retrospect, Daniel, do you think it's more understandable, the construction of p prime, if you follow the generator arguments that he has in like page 484 or 483? Does that start to make more sense to you, the way he... I mean, this is kind of like black magic or something, what I've written in the green, like why on earth are we doing that? To really take ownership of this algorithm, we should spend time to understand that. We don't have time this semester to get to that, unfortunately, but... What's that?
The first time we talked about this method,
Yeah, I suspect I have said things in the past which justify it, but me saying them and us understanding them are slightly different things, right? In any event, apparently, the calculations on page 484 would be analogous to the construction of p prime, except directly on generators, as opposed to, well, I don't know. So, I guess that's good. We have, I mean, to complete it, to be absolutely sure, I'd like to calculate P inverse and actually see that P inverse AP is, what it is. But you checked it? Yeah. I mean, but it is actually almost immediate from this. See, because if you look at P inverse AP, what you've got is you've got P inverse, and look at what this is. This P is what? It's a times x times a squared times x times a cubed times x, yeah? And so what is that? Well, that is P inverse ax, P inverse a squared x, P inverse a cubed x, right? And with respect to this coordinate map, oh, okay. Oh, I'm sorry. Go. So, fine. I'm actually not being sarcastic. But this is the second thing in the basis, right? It's that right here. So this is the coordinate vector of that in the basis. So that is 0, 1, 0. This is the third thing in the basis. So that's 0, 0, 0, 1. And this right here is, by the minimal polynomial, equal to 6a squared x minus 12a x plus 8x, which, again, by the coordinate map is what? 8, 12, minus 6. So I can calculate it without actually calculating P inverse as well. Of course, that does, I'm kind of assuming that things are working also, but anyway. Well, that was good. So I hope that that's enough to make this not a burden to you in this final exam time to make it do reading day. I think we should all be on track to have it pretty well done, and I would like for you guys to check with one another the G matrix, the group reduction problem, because I really want to know what the answer is. I made the problem up, and I reverse engineered it from, I want to say I think what I started with was like Z2, Z3. I think I started with that, and then I just wrote down the relations for it and did a bunch of stuff, come up with that matrix that I gave to you guys. But I feel like I think that was my intended answer, but that's not what I'm getting back to. So I don't know.
So you're going to be offended if we copy this problem now?
No, not at all. Not at all. Although if you'd like 10 bonus points, work this out for another matrix that's interesting. Yeah. 3 by 3. So. Yeah, I wouldn't mind having another example to use. So if you guys want to create one for me, I'd be happy.
I'm going to use the identity matrix. And you can take that back.
I said interesting example. I've already covered the bases. I for interesting. Jerk. See here. Anyway, guys, it's been fun. I will hopefully post like a little video talking about the solution when I finally have it all written. It won't be a long video, but just in case there's anything else to discuss in terms of problems on the test. And I guess if I was very, very energetic, I might post another video talking about solutions to problems in the homework. Given my current progress on things, I definitely can give you a few more days on the homework because I'm not going to post solutions for it. That'd probably be helpful to you if till Friday. Is that what I said already? When was your final? Monday. Yeah, I can. Well, if I don't post solutions before then, there's hardly any point of posting them. I better collect it Friday, otherwise I'll never write solutions. Let's make them do Friday in the interest of me actually writing solutions. I know myself at this point. Don't give me an excuse not to write them. Don't want that.